Welcome to this lecture. In the previous lecture, we had learned about the relationship of U and V to the displacements Q1, Q2. So we had U and V were given by into the column vector Q1, Q2, Q3 up to Q6. We also learned that for the same triangular element, the coordinates of any point could be given by x equals to n1 x1 plus n2 x2 plus n3 x3, and y of a point within the element is given by n1 y1 plus n2 y2 plus n3 y3. So the shape functions n1, n2, n3 were used for finding out the coordinates of a point as well as for finding out the displacement of a point within the element. Now, using these equations, if we replace n1 by zeta, n2 by eta, and n3 by 1 minus zeta minus eta, we will get x equals to zeta x1 plus eta x2 plus 1 minus zeta minus eta x3. Combining the zeta and eta terms together, so this x1 minus x3 is zeta, x2 minus x3 is eta, and x3 is a constant. And y we will get as zeta y1 plus eta y2 plus 1 minus zeta minus eta y3, bringing together the zeta terms and the eta terms, we get this equation. Now let us use the denotation xij equals to xi minus xj and yij equals to yi minus yj. So using this, we will get x equals to x1 minus x3 will be x13 into zeta, x2 minus x3 will be x23 eta plus x3. Similarly here, y1 minus y3 will be denoted by y13, y2 minus y3 will be denoted by y23 plus y3. So these equations of x and y, they relate the coordinates to the zeta and eta coordinates. So the x and y coordinates can be related to the zeta and eta coordinates using these two equations. Let us now move on to finding out the Jacobian of a triangular element. So in evaluating the strain, the partial derivative of u and v are to be taken with respect to x and y. So we had the previous from the previous lectures, we had equations 1, which was given by u equals to n1 q1 plus n2 q3 plus n3 q5, and v equals to n1 q2 plus n2 q4 plus n3 q6, and this set of equations that is here. Okay, so I'll call this equation A and this as equation B. So using equation 1 and equations A and B, we know that u is a function of x and y, which is in turn a function of zeta and eta. The same thing holds true for the displacement in the y direction, that is v. So let me call this equation 3. Now I am using the chain rule of differentiation. For the partial derivatives of u, so I get dou u by dou zeta will be dou u by dou x into dou x upon dou zeta plus dou u by dou y into dou y by dou zeta. Similarly, if I do dou u with respect to dou eta, I will get dou u by dou x into dou x by dou eta plus dou u by dou y into dou y by dou eta. If I have to write this in matrix form, it will be dou u by dou zeta, dou u by dou eta, and this is equal to the terms which are common in the equations above are dou u by dou x and dou u by dou y. So I write this in a column vector, and the remaining terms I have to write a square matrix. So it is dou x by dou zeta, dou y by dou zeta, dou x by dou eta, dou y by dou eta. So I'm calling this equation 4. So I know that this 2 by 2 matrix here, it's a 2 by 2 matrix. This is a 2 by 2 matrix, and we call this as the Jacobian of transformation. So this equation here is called Jacobian of transformation. That is because it's denoted by capital J. It's called the Jacobian of the transformation because it is giving the transformation from the zeta and eta coordinates to x and y coordinate. Okay, so J is given by dou x upon dou zeta, dou x upon dou eta, dou y by dou zeta, dou y by dou eta. Previously we also derived x in terms of zeta and eta, and I'm rewriting that equation here. Those were equations A and B, and y equals to y13 zeta plus y23 eta plus y3. Now dou x by dou zeta, if I differentiate this equation with respect to zeta, I will get x13. If I differentiate it with respect to eta, I will get x23. Same thing for the equation in y. So I get y13 and dou y by dou eta is y23. So substituting this in the J matrix, dou x by dou zeta is x13, dou x by dou eta is x23, this is y13 and y23. Also from equation 4, okay, so now we are taking the column vector on the right hand side to the left hand side. So we have dou u upon dou x, dou u upon dou y equals to, the Jacobian matrix will now be inverse, dou u by dou zeta, dou u by dou eta. Let me label this as equation 5. If I want to find out the inverse of the J matrix, it will be 1 upon determinant of J, which is x13 into y23 minus y13 into x23. Okay, and transpose of the cofactor. So when I do that, I will get y23 minus y13 minus x23 and x13. So this is J inverse. Let me call this equation 6. It can be proved that for a given triangle, the area of the triangle is half the determinant of J. This we will see in examples in coming lectures. So moving on, the points 1, 2 and 3 should be ordered in counterclockwise direction to obtain the determinant J as positive. This is one point that we need to keep in mind. So from equation 5 and 6, we have and when we multiply this, equals to 1 upon determinant of J and this I will call equation 7. We will continue with this derivation in the coming lecture. Thank you.